Bom, boa tarde para todo mundo. Fabrizio, I will introduce you in Portuguese, okay?
Okay, so that you can say everything you want. I cannot understand. Thank you.
Yeah. Okay, that's the point. Boa tarde para todo mundo. É um grande prazer para mim apresentar o professor Fabrizio Ruggeri. O Fabrício, ele é pesquisador do CNR em Milano, né? Atualmente, ele é vice-presidente da International Statistical Institute e presidente da International Society for Business and Industrial Statistics. Ele já foi presidente do ISVA, já foi editor-em-chefe do Bayesian Analysis Journal, atualmente é editor-chefe do Applied Stochastic Models in Business and Industry, tem mais de 100 artigos publicados, vários livros, inclusive um desses aqui, estou fazendo propaganda, tá? E Fabrício trabalha com diferentes áreas da estatística, tem muitas contribuições na área de robustez bayesiana, e na área de confiabilidade de processos estocásticos, então eu deixei ele livre para escolher o tema, mas não muito, tá? Fabrizio, thank you so much for spending your time with us. It's a great pleasure to receive you here. I will let you alone, and I come back at the end of the seminar, okay?
Okay, thanks a lot. Okay. Bom dia, muito obrigado. That's all I know about Portuguese, apart from Pau de Queijo, but it's another issue. It's a great pleasure to be here again in Belo Horizonte. Actually, I would have loved to be there, but this is life. What I'm going to talk tonight, tonight is for me, today is about a work done especially by one of my students, Anthony Ebert. I am also a adjunct professor in Queensland University of Technology in Australia, so that's part of my job there in working with students. So the work is mostly due to Anthony Ebert, who is now in Switzerland at Università della Svizzera Italiana. And the other co-advisor of the student was Kerry Mengers from QUT Australia, also Paul Wu from QUT, and also involved are Antonietta Mira from University of Insubria in Italy and Università della Svizzera Italiana in Lugano, Switzerland, and Rita Brattaduta, who is now in University of Warwick. The work I'm going to talk today is about likelihood-free parameter estimation for dynamic queuing networks, the case of immigration queue at an international airport. And I will start with a motivating example for this, which are queues at immigration control in airports. Then I will discuss a little bit about what queues and dynamic queue networks are. Then I will introduce you to the package that we developed called the Queue Computer to simulate queues. And then I will say a few words about approximate Bayesian computation and apply all of this to the immigration control, discussing also critical aspects and future and possible research. This is a nice example of a student who is doing not what the professor wants to do. So my original plan was to do a lot of work about decision analysis, decision theory, try to find optimal choices about the number of staff to put at immigration control and so on. But the students was not of the same idea. So he wanted to do something more computational. And then this is the result. So so we went in the direction he wanted. So ABC is something I had no clue what it was about. Now I have some knowledge, but not so much. But you will see at the very end, I was able to convince him to do something also about decision analysis, which is an area in which I'm more expert. These slides were prepared more than 1 year ago, so in January last year. It was before the pandemic, unfortunately, and talking about the great expansion of travel by airplane, the rapidly increasing number of passengers in airports, and I hope these figures will somehow come back to later on in our life when we will be still able to travel. By the way, in these days I was supposed to be in Brazil because of SINAP, but I hope I will come another time there. And there are a lot of critical consequences of the increased number of passengers. So there is more congestion in the airports. There are possible more flight delays, more pressure on the infrastructure of the airports, and also there are some capacity constraints due to about the future. And the interest of the work was having a movement of the passengers within the terminals which was smoother and quicker. So this was part of the project in Brisbane, which was called Wayfinding Bayesian Network Model. It was a part of the project called Airports of the Future, and there were different aspects of that. I was involved initially in one which was called Wayfinding Bayesian Network, and that was interested in investigating the factors which have influence on the way the people are finding their way in the airports, so the wayfinding in airports. We consider different aspects, human and environmental. And we built, actually, the people at QUT built a Bayesian network through focus groups. So we asked 99 people to fill some form, provide some data. At the end of the day, what they got was something like this. So let me change a little bit so that I will make this larger. So what we get is this Bayesian network. Why are the Bayesian networks so important? Because when you have a large problem with a lot of variables, this allows to split the problem in many smaller problems. And here there are all the variables which were somehow involved. The one in blue are somehow related to environmental factors. The one in purple are related to communication. The one in the pink are human factors. The one in green are navigation pathway. And this is the quantity of interest. So here you can see the relation. So for example, public address system is depending on language, audibility, clarity, and so on. And so there is a sort of relation, what is causing what. From a point of view of statistics and the probability, for those of you who don't know that, the interest is the following. For example, let's see the last three terminal nodes. What is that? There will be a good wayfinding given that the human factors are good and the environmental factors are bad. I'm just supposing that there are two possibilities, good and bad. So we have to build some conditional probability table telling what's the probability of good wayfinding given that the human factors are either good or bad and the environmental factors are good or bad. So for each node, we have to do something like that. And also we have to put some probability here about language and so on. So at the end of the day, with this kind of structure, it's possible to say something about a person entering the airport, knowing that her knowledge of language, knowing the purpose of travel, for example, tourism rather than business, the familiarity with the airport, and so on. Given all this data, we would like to know what's the probability that she will be able to find her way through the airport. So this is the way we use it. So for each one of this node, we build a conditional probability table. And here we had two possibilities. And now we go back to what it was before. And here we are. So the work I did was to build a Bayesian, to combine the opinion of these 99 experts. So the possibility is this one. At each node, we combine 99 conditional probability, and we get just one Bayesian network. The other possibility is that for each one of these 99 people, we build a Bayesian network, and at the end of the day, we will get 99 probabilities of the factor that we are interested in, wayfinding, and we combine them. The difference between the two of them is that one is called prior pooling and the other is called posterior pooling. There are also some other differences. And the last paper that we did on this was about a measurement error approach. So each one of these 99 values for each one of these conditional probabilities, so there are many conditional probabilities, as you can see, each one of them is equal to the true value plus an error. So we have this 99 observation for each one of these, and we got an estimate of the true probability. So this was some work we did. But the one I want to present today more is about what we did in terms of passengers arriving at the international airport and what we are doing at immigration. There are multiple stages which are through which the passenger go: airside concourse, then immigration, baggage collection, customs, landside concourse. But we are interested now in the immigration because we would like to predict what's going on, if there is congestion, how many managers, how many staff should be put on to check passport, and so on. So there are many issues related to this one, many reasons for doing this. It's important to do this simulation, what's going on within a terminal, for capacity planning of the control, operations planning, how many people to put there, and this one, the previous one, was how many, for example, smart machines to put there. Also some planning about security. Also, we would like to know something about the performance of the airport. But there are different aspects which are conflicting. For example, as a passenger, I would like to spend as less time as possible at the control. But from the point of view of the authority, there is a cost for having officers. So there is a cost availability of officers against length of queue. Also, there are other issues which are the complexity due to the number of passengers and incoming flights. So there are issues related to where the flights are arriving in terms of gates, the waiting on board. Sometimes people are kept on board just to avoid congestion at the immigration control. There are many, many issues. And also there are possible changes. You will see at the end of my talk a study about a possible change, what's going on. So we need something to do, a quick online inference for day-to-day decisions. I will tell you that we developed a very nice model, but it's not been applied so far by the airport I'm talking about. And there are a lot of studies about issues related to airports, about flight delays, gate assignment, runway queuing, performance evaluation, effect of global airport network, global epidemics. This was written before the pandemic, and you can see the relevance of this, security systems, passenger walking speed, and what we did about passenger wayfinding. And so the idea here, the goal is based on past data and the knowledge that we have about the flights which are arriving. We would like to find the optimal number of officers to put in charge of immigration. The issue here is if we were able to build the likelihood, then things would be easy, not simple, but easier. In the sense that it's not possible to build a likelihood. I will show you later why. And in this case, with the lack of a likelihood, we are going to use a method which is getting more and more popular called approximate Bayesian computation, ABC, to simulate the data. The point is that the simulation is very computer demanding, so we need some simulation which is fast. And for this reason, we developed this code Q computer in R, which is available in CRAN, which is reducing a lot the simulation time with respect to existing other codes. And there are also other issues related to conflicting utilities, passengers waiting time with respect to cost of the officer. So that's something else. So this is essentially what we have, a scheme or what we have, the data that we have, and the process which is going on in the airport. So here you can see different gates, A1 to A29. And this is the gate in which the airplane arrives. And then there is a time for people to disembark the airplane. We call it T1 DIS. And here there is a camera capturing the number of the people who are passing there. So counting the number of people who are passing there and also the time in which they are passing. This one for each one of this gate. Then there is a time to go to the immigration area, and this is T1 AC. And here there is another camera which is capturing the people who are entering the immigration area. But you can see we are losing the knowledge about the flight people come from. So this is one of the points which does not allow us to have a likelihood. Because if you could follow a person from when she disembarked the airplane to when she leaves the immigration area, then it will be very easy to follow this person at step by step, because we are able to model each step by using a distribution, but unfortunately we don't have the proper information. And then once the people are arriving at the immigration area, they can choose, more or less, they can choose if to go through a manual gate or a smart gate. Manual gate, you have to go through to show your passport to an officer. Smart gate, you put your passport in a machine. When we started this work, this was in Australia. I cannot tell the name of the airport, but you could guess. When we started this work, only Australians were allowed to go through the smart gate. Now, now before the pandemic, also other nationalities, including Italians, could do that. But in that case, it was only Australians, so you can choose there. And of course, there are different service time if you go in one direction or the other. And then there are cameras capturing the people who are leaving the smart gate area and the people leaving the immigration area. So so the data are, as you can see, are not exactly what one would like to do, a perfect likelihood-based estimation. So here are the kind of data, 3 times during the day. Here you can see the straight line, vertical line are the times in which the airplane landed, and the size of the line is related to the number of people in the airplane. And then the other one, which is jump up and down, are the number of people who are entering the immigration area. This is the overall, and this is the one entering the manual gate and entering the smart gate. So this is the kind of information that we have. And then we have the similar information when they are leaving the immigration area. So this is essentially the same. So what is now a queue? So now we are considering customers, in our case passengers, J, which are entering a system at arrival time A sub J, and they require a service which is whose length is S sub J with a server. For example, customers in a bank, patients in a hospital, and passengers at immigration control. So we have arrival time and service time. And we build a vector of all the arrival times of all customers and the vector of all the service time of all customers. And typically a server can serve only one customer at the time. And this server can be unavailable or available for other customer if it is serving a customer or not. But so we have also that the customers have to wait if all servers are unavailable. And then we have waiting times, which we denote by W. And Wj equal to 0 means that the customer, when she arrives, she's immediately served. So at the end of all this process, there is a departure time from the system, which is D sub J, which is the sum of arrival times, A sub J, waiting time, W sub J, and S sub J, which is the service time. So this is what we have. And there is a conventional way of describing a queue. It goes back to Kendall in 1953. These are these 6 characteristics. And the first one is about the arrival process. Which kind of arrival process there is? The service process, the number of server, the capacity of the system, which could be finite or infinite, the size of the population, which could be finite or infinite, and the service discipline, which could be, for example, first in, first out. The simplest examples are MM1, so exponential arrival, exponential service, or if you prefer to say homogeneous Poisson process, with just one server. Or a general independent arrivals, or and here we have C servers. Here is again a general service time, and this is both general arrivals and general service. So these are the most common ones. And what are the quantity of interest in this case? Well, we are interested in estimating the parameters of the arrival and the service processes. And from a point of view of the customer, we are interested in the waiting time in queue, the size of the waiting queue. From a point of view of the one providing the service, so the servers, we are interested in the busy period, so how much this is working, and the idle time between services, so for how long the server has been doing nothing. And there is a need to introduce some performance measure. There are very nice books about queues and that. you can read more about that. So from a point of view of Bayesian, because I'm taking this from a Bayesian point of view, the first work goes back to Noza Simpurvala. But the people who gave a great contribution to the development to the Bayesian approach in queuing are Carmen Armeron and Susi Bayarri, who at the beginning of the 90s did a lot of work. We started with MM1. And then also myself with my friends David Rios-Insua and Mike Wiper did a lot of work. The most relevant is this one about MG1, because we used also a mixture of gamma distribution to model this G. And there are other works even later on. Now, as I said, the likelihood function is unavailable or very difficult to derive, like in our case. So which kind of simulation method we could use? Well, it's very popular, the use of discrete event simulation, in which we are simulating inter-arrival service times over a sufficiently large time period. We have to get rid of the initial times, but then it will work, going away from the transient behavior. Or there is approximate Bayesian computation. I would say that our work is the first work, as far as we know, about the use of approximate Bayesian computation in what are queuing networks. So queuing networks are a network of queues, as the word says, and dynamic queuing networks in which something changes. In our case, what happens? We have flying in different time of the day with different number of passengers, so it's a dynamic queuing network. Queuing because we have to go through different steps, leaving the airplane, reaching the immigration control, going through control passport, and so on. So here we developed this software where most of the merit goes to the student, Anthony Ebert, which uses an algorithm which we call the queue departure computation. And this is a very, for us, computationally efficient method for simulating departure times for a lot of different kind of queues. We compared, I will show you also later, it with other very popular discrete event simulation packages called Simmer and SIMPy, and we show that our code is twice faster than them. Where we did some validation of that for making such a statement. And this Q computer code is very important in what we have done about the application to queuing network. You will see later. So here I would like to see the key idea behind the Q computer. How to generate departure time? Well, there is a way, an algorithm developed by Lindley, the famous Bayesian, long time ago, 70 years ago, in which essentially we have the following. For the ith customer, we generate the arrival time, A sub I, the service time. The issue is how to generate the departure time. The formula is very easy. It's D sub I, departure time, is the maximum between A sub I and D sub I minus 1 plus SI. What does it mean? Well, SI is, of course, is the service time. But this maximum, well, there are two possibilities. We are talking about the case in which there is only one server. So when the new customer, the ith customer, arrives, she can find the server either busy or idle. If it is busy, the server is busy, she has to wait. How much has she to wait? Well, until the previous customer leaves the system. So D sub I minus 1 is the time in which the previous customer leaves the system. If at that point the service starts. If she finds nobody being served, and then the time is just her arrival time. And this algorithm has been extended more than 40 years after by Krivul into the case of more than one server. And we can use this for different cases. Series queues, parallel queues, queues which are called fork join queues, in which there are tasks in parallel, but to leaving the system, you have to perform all of them. This is a different respect to parallel, in which is enough that you perform just one task. And here is and we can apply it to many different kind of queues, our queue computer, general arrival depending on time, general service depending on time, and so on. It works well when we fix a priori the number of servers. I will show you very quickly what happens when we change the number of servers over time. It's possible, but the best is when we fix a priori that will be a fixed number of servers. So our goal is to generate, as I said, departure times. Here we take a different perspective. We consider now for the client, the customer, when she arrives, the customer arrives, we look at the K server. So now we are in the case of K server, and we look for each one of these K server, little k, we look at the time in which the server will become available. Given that we are talking about the ith customer. So for each customer, there is this vector, which is updated. So what is the optimal choice for the customer in this case? Well, looking for the server which will become available first. So we look for the BI, which is the argmin of the BI among them. So DI is the maximum between her arrival time and the time in which the first server, when she arrives, will become available, plus the service time. So this is, this BPI could be the time in which a previous customer will be released, served by the system, or there may be a queue. There may be 3, 4, 5 customers waiting allocated to such a server, but that will be, in any case, if there are 4 or 5 customers allocated to that server, that will be the faster one for the customer which is entering. So instead of having before a matrix, because before we had, with the previous algorithm, we had to keep track of all the story of all the customers in the past, so huge matrix and so on. Now we have just to keep track of this vector. So that is simplifying things. And here we can divide the interval of time in which you are going to generate arrivals in blocks, in intervals, and each one of them we can change the number of servers. The code will be less efficient, but still is working. So now you can find also the Q computer available at CRAN, and that's all. And here is what we did. We had an MM2 queue, that means exponential service, exponential arrival, and 2 server. And here we have a number of customers, which is increasing. This is 1,000, 100,000, 10 million, something like that. And we run for each one of this number of customers, we run 100 of times our code, and also the SIMPI and the SIMMER code. And here you can see the median time of this 100 runs for each kind of customers, and you can see the computation time. Our is this one, and these are the other 2. So you can see that we reduced by half the computing time. And we get the same departure time. So that was itself the validation that we did. And this is the kind of information that we could have. We have from the system, from the computer. In red are the customers in the system, and in blue the customers are in queue. For example, here there are 5 customers in the systems and 3 are in queue. I remind you, there are 2 servers. In this case, here we have 2 in the system and none in the queue, and so on. And here we have 1 in the system and none, of course, in queue. From the point of view of the customers, here you can see in red this when she is served, and in blue when she is waiting. So the first one is served up to this point, then there is a second one entering from here to here, and then there is a third one entering, and she has to wait until one of the 2 servers is released, is available to her. So this is the blue part. As soon as the second one leaves, she is served, and so on. So this is from the point of view of the customer. From a point of view of the server, of the 2 servers, the blue part is when there is a service, and here, when there is nothing, it means that the first server number 1 is idle. So this is the kind of information that we get by using our Q computer. Now, looking at our problem, so if we were able to have the likelihood distribution with our prior, we could use Markov chain Monte Carlo, the usual method. The point is that here we are not able to get the likelihood. So what is the idea behind the ABC? I'm not an expert in ABC, but what I learned is everything I put here. So Anthony is the very expert on this, my student. And the idea is the following. We have some data, we call them Y. These are the data that we have observed, which are the data captured by the cameras I told you before. And now we are able to generate data. We are able, because I told you, we have the model to generate arrivals times, to generate times from the airplane to the immigration area. We have a model to generate them. So what we do is the following. We also have prior. So we get the value from the prior, and then we generate new data, and then we compare the new data, the simulated data, with the real one, the observed one. We need to introduce a distance between the two data, between X and Y, and we accept theta star if this distance is less than epsilon, so they are close, because that means that the theta belongs, I'm saying roughly, to the posterior distribution. So it's possible to see that if we keep this theta star, which are generating values of X which are close to the real values Y, then we get a distribution which is close to the actual posterior distribution. I think there are theorems showing that if we let the epsilon go into zero, we get something like that. The point is, can we measure the distance between data which have a dimension which is a very huge one? It's very difficult. So the idea is to use a statistics S, and apply this distance to this statistics. You will see which one we use. The point is that with the statistics is reducing the dimension, makes computation easier, but we are losing some information. Which kind of distance we use? Well, we tried others, but the one at the end of the day we decided to use is the maximum mean discrepancy, which is given by this one. So we have two random variables, X and Y, and a class of function. This is defined as this soup. And of course, this is not useful for our computation, so we need some estimate of that, and this is the one we were able to find. So we use this estimate to see if the sample that we generated with this value of theta star is close or not to real data, and we build our posterior distribution in this way. So this is just a toy example to show you how things are working. So here we have an arrival times according to some distribution. And then here the passenger can choose to go in one direction or another one. And here there is a Bernoulli distribution ruling this decision. And then here there are times to go from, this is from the gate to the immigration area, which are T naught, and then the people arriving at the person is arriving at the immigration area at the time D naught A, or if she goes the other direction, this is the arrival time. And here we're going to use a gamma distribution with the same parameter for the two of them. But then once they are here there is a service, and the service depends on the speed of the manual or rather than the smart gate. And here we have two different exponential distribution, and here and the person are taking service time S0 or S1, and here we are observing the departure time. So in principle, as I said, we have all the distribution. We have a density for the arrival, we have a Bernoulli, we have a gamma telling us how to arrive to the immigration area, and then we have two different exponential distribution. We know also the number of servers in the two routes. So in principle, we know everything. But the point is that we don't have the proper information. So how can we use our QDC? Well, in two ways. One could be fixed, one is more probabilistic way. We fix the parameters of the process, and then we compute and do simulation, and we compute the measures, the performance measures, like length of queues, waiting time, number of customers in the system, idle periods. So this is the more probabilistic use of our simulation tool. The more statistical one is, well, we have the data, we want to estimate the parameters of the Bernoulli, the parameter of the gamma, the parameter of the two exponential. And for doing that, what we do is to simulate the data. And here is the role of QDC, of our computer code, which is relevant, because we have to simulate data. And you understand that you have to do that thousands and thousands of times, and having a computer code which does the job in half the time than the previous codes makes things definitely better. So this is the point in which our Q-computer code is used. So this is the picture that we already saw, and now these are the real data. So we have 29 flights and more than 5,000 passengers. We have information for each flight about the arrival time, the distance from the arrival gate to the immigration control, the number of passengers on the flight, and the percentage of passengers who are Australians in this case, remember, for the reasons of choosing the smart rather than the manual gates. We know also the number of machines at smart gates. We know also the number of staff members at manual gates. And these are the data that we have. I understand it might be difficult to see, but what you see is similar to before. Now we put some color. Why we put some color on this vertical line? Because this is essentially the proportion of Australians related to the proportion of Australians. This flight has most Australians. This one has very few Australians. And the black ones are against the people who are entering immigration, and in general, the manual gate, the smart gate, and also leaving. So this is the kind of information that we have. As I said, we can build the model. Disembarkation times are gamma. Time to the immigration control, gamma. Distribution about being national foreigners, Bernoulli. Selecting one of the other gate is another Bernoulli. Service time is exponential depending on the selected gate. We can put also vaguely informative prior. You can see if we could observe for each person air disembarkation time, air time to immigration control, everything here, we could build the livelihood and we would be very happy. This is not our story. So we have to use the method that I'm proposing. So I'm left with 10 minutes and 10 slides, and so we are on time. So we did 3 analyses. One is a synthetic, one with real data, one with realistic data. Why the 3 of them? Usually when you propose a new model, you try to show the entire world that your model is working and is working very well, in the sense that you generate data from parameters that you know, and then you show that you get a posteriori the parameters from which you generated the data. So we want to check the validity of the model. Of course, you have to apply also to the real data and see what's going on in reality. But then there is another issue about journals. The journal to which we submitted the paper, which is giving us some troubles, the journal, I mean. Hopefully we will solve them, because they solve them pretty soon, because they ask a lot of revisions. So the problem of the journal is that we would like to publish the data, because the idea is to have a research which is reproducible, so that the other people can test if what you did with your model is exactly what you are presenting in terms of result. The point is that these data are not available to the public. So what we did was take the real data and modify that and make them realistic. And this is what we did. So I start with the simulated data, and here we are interested in 4 quantities, which is the service rate of the manual gate. Remember, this was exponential. The service rate of smart gate, against exponential. In terms also of walking time, it was a gamma distribution, but we modeled the gamma distribution in terms of 2 parameters, which were the mean and the standard deviation of this gamma distribution. And here you can see the red vertical line, which is the true value of the 4 of them. And you can see the median, which is the dashed one, which is very, very, very close. And we build also 95% credible interval. So here I'm showing you that our method is working, at least with the data that we have in this example. And then this is the real data. Of course, here we cannot compare with the true value. So here, this is the kind of information that we can provide. So the service rate of the manual gate has a median, which is 1.2, and the smart gate is 1.7, and so on. So this is the kind, and this is also the 90% credible interval, and these are also the posterior distribution of our parameters of interest. And these are the perturbed data. We did the same with the perturbed data. Nothing different. And this is what we did. It's important is that, for example, posterior predictive distribution of something. In this case, of the walking speeds. Here we did with the synthetic data. We did the following. we build the posterior predictive distribution by using the true parameters for which we generated the data, and you will see the blue line. And then we estimating using our methods the parameters by using ABC, and we did the same. So we got the predicted distribution based on our estimated parameter is the red one, and here you can see a slight difference here. So essentially, we got essentially the same. And also, what we got in terms of estimation of walking speed is similar to what we found in literature about similar problems. And this is another way of validating. Sorry if you can see very well. So we have the real data, which are the black one. And then we build predictive intervals based upon our estimated parameters. So we will predictive intervals, which are 95% prediction interval. And you can see that, well, you can see more or less, you can see that the actual data are essentially within the predictive intervals. There's another way of validating the work. And this is for a future customer. We try to predict what is this? The waiting times for a new passenger. So here the black line in this case is the median of the predicted distribution, and this is the 80%. The light blue is the 80% predicted interval. And here is the last case. I'm considering that eventually we arrived to the decision analysis part I was interested. So let's suppose there is a normal case in which predictions are following from planned flight schedule, nothing bad happens, but then there is a disruption. The second flight is delayed by 15 minutes. What is the consequence on the migration control? Well, the median waiting time goes at 10:50 in the morning, goes from 28 to 71 minutes, and the median queue length from 146 to 363 passengers. So how can this code be used? Well, moving people from to staff from the earlier to later shift. So we are moving, you will see later the picture. So there is a decrease of median waiting time to 41, so from 71 to 41. And the median queue length from 363 to 319. Well, not much, but it's something. So this is what's going to happen. So this is what was supposed to happen if nothing bad was going to happen. The straight line, vertical line are the flights which are arriving, and the size of the line is based on the number of passengers on the flight. And but then this is the second flight is delayed. So what's happening here? Here you can see up to this point, there are 15 people in the smart gates, and then here 4 are planned. This is what you can read in this gray line. And then what is this red one? This is the prediction intervals for waiting times, a 95% prediction interval for waiting times at the manual gates. But then the flight here is delayed. So what's going to happen here? You can see a huge jump of the prediction intervals. But then here there is a change. We are moving to people from earlier. So now there are no more 15 here, but there are 13 years. And here there are 7. And here you can see a little bit worsening here, but this predictive interval is getting better than what have been done there. So this was the idea which I was interested in. So find the optimal number of officers. And just to conclude, there are some issues here. Sometimes when we are generating data from the ABC, we get distributions which are some peak, which are a little bit delayed with respect to the real one, and we are working on this. Also, as I said before, we could have used different measures to measure the distance between the generated data and the real one. We could have used the Wasserstein distance. It didn't work very well in this case. We could have used also applied our process to different kind of queues. We did adjusted immigration control. And then, so what are the issues about future and possible work? Well, optimal allocation of resources. You saw just an example before. Also, there are conflicting interests, and that can be modeled by using the classical multi-criteria decision analysis, or something else I'm very interested nowadays, which is adversarial risk analysis, formalizing as a game between resources, planner, and incoming passengers. Also, of course, the choice of the priors is something of interest, as Rosangela said, understood something of almost everything she said in Portuguese, by the way, in terms of changes in the priors and the sensitivity to such changes, something which is, we call them Bayesian robustness. Also, as said, just said, there is an importance about the optimal distance to be chosen. We chose the MMD, but we could have chosen something else. We could have used something else in terms of other kind of cues. As I said, the shifts of the peaks is something which is creating a lot of problems. So there is a need of registering the curves. And we are working on that, but this is a very tough work we will do in the future. And these are essentially our work. So the Q-Computer package is not only in CRAN available for people to use, but also is described in this paper, which has just been published in Journal of Statistical Software. And then the paper I presented today, which involves also Rita Brattadutta and Antonietta Mira, is under revision for a journal. And then the part about the wayfinding, so the Bayesian network, is part of a dissertation of Charis Farr, and it's been published in two journals, Entropy and International Statistical Review. I would say that's all, and I'm ready to get questions. And I don't know if I have to give the screen back to Rosangela or not.
No, it's Thanks. Okay.
Okay.
Thank you so much for your talk, Fabrizio. Is there some question or comment? As there is a delay, Fabrizio, I have a question. I don't know ABC very well, but when you define, you should define a kind of distance. Can you give you some guidelines on how to choose this distance? Or there's a big influence in the posterior result if you decide for another way to measure this distance?
Okay. I started, usually when I give this talk, sorry, this is my, okay. No, that was my timer telling me the 45 minutes, okay? Sorry. When I start this issue, the talk, usually I say, I'm not an expert of ABC. Ask Anthony Ebert about this. But I will try to answer your question. I'm not an expert of ABC. I don't know much about it. But the point is, what we did here was to use at least these two measures, the MMD, and we try to use also the Wasserstein distance. The point is that by using, I don't know if there are theorems. I don't think there are theorems. Someone in the audience might tell something about that. Theorems telling you when to use what to use when, sorry. It was also good the other way. In our case, we did the following. The Wasserstein distance was not good to get a good reconstruction, good distribution, especially when we did in the simulated case. The MMD was able to get us good results in terms. I showed you that the median we were able to estimate was very close to the real value of the parameters, and when we did with the Wasserstein distance, it was not that the case. So this is the one we chose is the one which worked the best. Okay, from an empirical point of view. If there are reasons to choose one or the others, I don't know. As I said, this is really an issue also raised by the referees of our paper. But MMD worked. That's the issue. Wasserstein did not.
Well, I have a question here from Marcus Prax. I don't know if you can read it or not.
Let's see if I change to some. Where should I go? Should I go here? Let's see.
Can you read?
Sorry. How
can you also determine if the use the distance is optimal or even better than the one you used?
Okay, thanks, Marcos. I repeat my answer before. We tried this one, and I think Anthony tried also other besides these two. And as I said, it was just an empirical decision to choose MMD. It works, and it was easy to implement because the estimator that I show you is very easy to compute. It was it was like that. But you should ask Anthony, or maybe Carrie, Antoniette, or all the others. I am the decision theory guy in this group, okay? And the Q guy. So my contribution were about Qs and decision theory, not about ABC.
Okay. Marco said that in my little experience, the choice is usually empirical.
Thank you, Marcos. We should have avoided such a question. Give immediately your answer.
I wonder if there is a more theoretical and generic way.
I don't think so. Okay. For my knowledge, I don't think so. But as I said, I'm not an expert. If other people like Egibert Lopez is here, he might know better, for example.
Okay, if you discover the way to decide about that, I would like to know. Okay. You too. You and Marcus, do you know?
Okay.
Is there any more question or comment? Mariana, do you have any question? Today you have another, I invited a lady in our seminar, in our room.
Yeah. Well, if you want, I can tell you where my sweater comes from, okay?
Okay.
The sweater comes from Porto Alegre. It's a Brazilian sweater. It's the last time I was in Brazil, I bought it because my luggage was left somewhere by Lufthansa. So I had to buy a Brazilian sweater, and I like it a lot, okay? I like also a lot of Brazil, by the way.
Blaming me because of that until today. It was 2016. Come on.
Now it's clear.
I have questions. I don't know if I understand completely, but I would like to know if you incorporate some dependence among the observed variables in the model.
In the the notion of dependence, independent. So when we generated, they were definitely independent. Yes. Well, they were somehow independent. So all the times that we generated are independent. As I said before, there was a gamma for, so when we generate, okay. So we generated the, yes, the arrival times, not arrival times, the disembarkment times independent. Yes, it was, everything was independent. Yeah.
I think Nancy Lopez is thank you for the presentation.
Okay, thanks, Nancy. Okay.
And I guess, Fabrizio, that is all because I don't have any more question here. I just like to thank you again for giving us a talk. People need to know that I just invited you 2 weeks ago, and you were so nice and kind friend to accept my invitation in such a short time.
Okay.
Thank you so much.
It was a great pleasure, but next time I will do that in Belo Horizonte, okay?
I hope so.
Okay.
Nancy has another comment here. Look.
Yes, you are completely right. Also, an issue Definitely, we may need to have clusters and also Poisson process. One of the criticism of the referees was about the fact that we didn't use a Poisson process. The point is that the data are not allowing us to consider the Poisson process in a proper way, because we are not able to follow the people. So if we had people going from just one airplane to the immigration area and leaving, that could have been possible. But there are a lot of issues about the use of Poisson process. Also, by the way, there should be non-homogeneous Poisson process because there is a change over time. Also, actually, the referee asked us to use a Poisson process. The point is that there are clusters, not only clusters, but there are bursts. So there are a group of people passing at the same time through the same place. So the Poisson process is good to model events which are rare. So, and here it's the events are not rare. But even the clusters, if we use the Poisson process to model clusters, not even them are rare, because of the fact that there are airplanes arriving, and then there are some points in which people are arriving in groups. Also, there are families which are passing on. So it's there are other issues which I wrote just a few days ago to reply to the referees about this. But the non-homogeneous Poisson process are easier. Actually, I used a lot of non-homogeneous Poisson process in my life, but I don't think you are able to follow the behavior of the people in this case.
Is there more question or comment? Is it okay, Nancy, or you have some more question?
Okay.
I guess it's okay. Fabrizio, then I will thank you again.
Thanks a lot. So
I hope I can see you this year, no, or next year. Thank you, everyone, for participating here. We received people from other universities, Mariana, Nancy. Very nice to see you here. Thank you so much. There's another comment here from Nancy, just to thank you.
I completely agree with you.
Yeah.
Nice.
Então, gente, a gente se vê na próxima semana. Muito obrigada pela participação. A gente se vê, tá? Bom fim de semana para todo mundo. Se cuidem, tá bem?
Ok, bye bye. Buonasera.